Hey, this is Train of Thought Science. I'm Shannon. This is my genius son Isaac. And our subject tonight will be the 6 states of matter. Eight states of matter. He did the homework, I didn't. But anyway, Isaac, I think we're going to be starting with the most basic states of matter most people are familiar with, right?
Yeah.
And the first one's going to be?
Solids. A solid is just a state of matter that does not change unless it's acted upon by an outside force, like the decay of wood or a piece of wood breaking due to gravity. But if it's in space with absolutely no bacteria to decay it, then it's not going to change at all. And a liquid is a state of matter that conforms to the container that it's in. It flows freely but has a constant viscosity. The viscosity is the thickness of the fluid. Just scientific measurement. The higher the measurement, the thicker the fluid is. And the gas is a highly energized state of matter that composes the atmosphere, and it's usually very thin, and there's a lot of free space between the particles because it's a bunch of small particles flying over them.
What usually brings about the state of gas? Temperature?
Yes, temperature. Okay.
Okay, I think we just got back. Well, the different properties or different states of matter that we were starting with isn't so much what people are most familiar with, but is the fundamental states of matter.
There are four fundamental states of matter. Most of us are familiar with the first three: solid, liquid, gas. But the next one is plasma.
Let's go back to gas for a second. How does gas usually come about? Is it because of pressure? Is it vacuum, or is it temperature?
It could be pressure or temperature. If the pressure is little enough, then it allows for an easier evaporation of substances such as water. But if the temperature is high enough, no matter how intense the pressure, it will evaporate.
Okay.
So plasma, there's actually a layer in our atmosphere, the ionosphere, is made of plasma. And
all of our ionosphere is made of plasma, or is it just when it's excited by the high energy rays?
It's just that plasma occurs in it.
Okay.
It's created by the ionization of particles, usually in gas. Ionization is the separation of the electrons from the nucleus. And
as a good example is the Northern Lights. Right. The Northern Lights are plasma. It's invisible, when we can visibly see the plasma.
Oh, and a lot of people that I know wonder what state of matter fire is. That's plasma.
Which I found out recently, I was pretty amazed with. I figured I would have known that one already. It seems so simple, but wow. Okay.
Yeah. And then so we've done 4 states of matter. We have 4 left, and then we'll add 2 side points. So the next is a Bose-Einstein condensate. It is the coldest state of matter. It forms at 0 degrees Kelvin, which is another temperature of measurement, such as Fahrenheit. 0 degrees Kelvin can also be considered absolute zero.
For the audience's sake, what would be, let's say Fahrenheit, what would 0 Kelvin be in Fahrenheit?
Negative 459.67 degrees Fahrenheit. And for Celsius, it's negative 273.15.
I was about to ask you that. Okay.
Okay, so it was theorized by Nate Bose and Einstein in 1925, but it wasn't actually created in a lab until the late 1990s. There are a few neat effects at this temperature, at the state of matter. The atoms and the particles have what theorists will explain as an identity crisis, where it looks like they're all merged together. It looks like this particle is over here, and every particle is every other particle. It's really weird. But this matter has been used in labs to slow light to the speed of a bicycle.
I thought they've actually been able to stop it.
Yeah, and crystallize light. Not physically where you can push it, but stop it. Just completely stop photons. And we'll get to what state of matter photons are in a minute.
And a little tidbit of information. The speed of light is not always constant. The speed of light is constant in a complete vacuum. light can be slowed down.
What we just say light years.
Light years?
The measurement of light.
Yeah, sure.
So, just for the sake of it, a light year is 5,878,499,814,210 miles.
He's showing off.
Yeah.
Okay, well.
Okay, so
next state of matter?
the next two are super solid and super fluid. Like I said earlier, viscosity is a measurement of consistency of a liquid due to internal friction. And the lower the number, the thinner it is, and the higher the number, the thicker it is. But super solids and super fluids both have zero viscosity. Both have zero viscosity, which means that they are almost completely thin. Like thin, thin liquids, water is thinner than blood, and it's zero is just ridiculously thin. And the fact that a super solid can be so thin, a solid can be so thin that you can pass your hand through it without making any effects. So a super fluid just has zero viscosity.
I've got a question. If it has zero viscosity, especially being a solid, let's say, can I shoot a bullet through it at, let's say, 10,000 miles an hour and there'd be no effect whatsoever?
Well, it would definitely push particles out of the way, but
yeah, but if
still
there's zero viscosity, that means there should be no friction. If there's no friction, there's no effect on the bullet
probably,
or the solid.
Probably, but it's still a very mysterious state of matter.
So scientists don't shoot bullets at it and stuff.
Doubt it.
No, they don't carry guns.
No. Okay, so the neat thing about a super solid is that it can keep its shape like a solid unless it's acted on by an outside force. And what we mainly make super solids and super fluids out of are helium. We cool it to the same temperature as a Bose-Einstein condensate.
Ever make a solid out of helium?
Super solid and super fluid. And our next is the state of matter called energy. This is what light is. It's just all matter is energy, and they can be transmuted into the other. So once you get a couple of particles to a high enough vibration, because vibration is energy, once they get to a high enough vibration, like when they collide, it'll appear as though some of the mass disappears, and that's just the mass turning into energy. So some examples of energy are light and electromagnetic energy. And something,
No, go ahead. I was gonna go ahead.
Oh, okay. There's something neat about electromagnetic energy. When you're playing with magnets, north attracts north, north repels north, south repels south, and north attracts south. This is because of the electromagnetic vortex. If you imagine a magnet, north-south, there are actually vortexes spinning in different directions on each side. Well, vortexes of energy. And the attraction is actually when the south side of one magnet is flipped over, the spin of the two vortexes line up and pull each other
So
in.
south to north. They
And
fit
our
together like pieces of a puzzle.
Yeah. And our last one is a droplaton.
And that's why when the magnets pull to one another, they're not satisfied with just setting like this or setting like this, but what they want to do is find a very specific spot where the vortexes meet up perfectly.
Yeah.
Yeah.
And then our last one is a droplaton. It's actually a quantum state of matter. Did we define quantum in our earlier video?
Yes, we did.
Okay, but just for quantum is something that's smaller than microscopic, so electrons and stuff. Electrons make up atoms. It's a quantum quasi-particle. That means that it's not a fundamental state of matter. It just stands at the side. Doesn't play any important roles. But it's actually a quantum quasi-particle that acts as a liquid. But if you think about it, liquids like water are made up of molecules. So the fact that you can have something on a quantum level that has a measurement of viscosity that can flow is actually pretty neat.
That makes a quantum quasi-particle.
The quantum is a size, the quasi-particle is a...
Right. Base words. But, yeah.
Okay,
Just awesome. Is that it for tonight? Let's see. Energy. We asked about energy.
Pause.
Yes, I had a question. I didn't want to interrupt you, but I had a question about energy. And we were talking about light being the energy, the opposite, the other form of matter. Energy being matter, or but if light doesn't have any mass, right? Okay. How do I ask this question?
How does it bounce off matter? Is that what you're gonna ask?
But this can go on to something new. Light doesn't have mass, but light can actually push a solar sail. How does that come about? If something doesn't have mass and it's actually moving through space, how does it push a spacecraft?
How? You've done more research into this.
Momentum. I can't really go into the science of it real good, but it's got to do with momentum. And it's such a tiny, minute amount of momentum per particle, not particle, but per photon, that for you to even be able to push a small spacecraft of a couple of pounds, you need an extremely large solar sail. But in theory, well, it's not even theory anymore. You can get near the speed of light with a solar sail with a small enough. If you have the size of the solar sail is balanced with the size of the craft that you're trying to push, you can actually get near the speed of light with it. It takes a long time, but it's potentially a real way to do what do you call travel in between solar systems? Interstellar travel.
And just for clarification, a space sail is like a sail on a sailboat, but for space.
Yeah.
Very complicated.
Yeah. But anyway.
And something neat about light, big cities that have a lot of structures and stuff actually weigh more during the daytime because of the photons striking them. But photons don't have mass. So all the photons from the sun striking down on such a large surface area such as New York or Manhattan makes a city heavier in the daytime.
Yeah, we're talking about less than a pound, but it does do it. Somehow they measure it, but well, not specifically a city, but they have made the measurement. They do know that light striking a surface, if it's working in conjunction with gravity, it will make a it will make a difference. Okay, well, anyway, I believe we're pushed for time tonight, and that's our talk for tonight. And we'll see you next time.